Hi, my name is Sandra Toledo-Rivera and I'm based in Anton Nikolaev's lab at the University of Sheffield. Today I'll be sharing with you some of our findings on visual adaptation in late-stage zebrafish larvae. It is well known that the visual system has evolved to fit specific needs in order to give survival advantage across the species. Vision is given by light, or in other words, the result of photons being transformed in electrical impulses through the retina. There is many information regarding the retina and other structures receiving the light input in many animal models. For instance, we know that humans and zebrafish share some similarities. Here we focus on the visual information reaching the deep structures of the brain. In mammals such as humans, most of the higher processing travels from the retina all the way to the occipital neocortex, passing through other deep specialized structures such as the superior colliculi, which is a structure in the midbrain in charge of the visual reflex response. The optic tectum would be the equivalent area in zebrafish. This is a complex system formed mainly by the series of layers of axons from multiple inputs, creating the opal-shaped neuropil encapsulated by a dense concentration of neuronal bodies which send information to deeper areas of the brain. In these experiments, we performed 2-photon in vivo recording of late-stage zebrafish reporting bineuronal calcium indicators while being presented with different visual stimuli in one eye. In the first case, a black circle moving unidirectionally across the screen 4 consecutive times, followed by a 30-second rest per 10, was used to assess general adaptation dynamics. In further experiments, we presented alternated sets of moving ratings varying in frequencies and contrasts. Then, we analyzed the distribution of the responding voxels to characterize them according to their specific fine-tuning and adaptation dynamics. We found out that the zebrafish brain areas exhibit different visual adaptation degrees. The optic tectum and pretectum exhibit robust depression, whereas the lencephalon, both avenula and the hindbrain exhibit quick adaptation or even facilitation. Adaptation was particularly strong in the ventral layers of both contralateral and ipsilateral tectums. This makes the visual responses in the output areas adapt nearly completely after the first presentation of the stimuli. Additionally, we find out that despite the layered organization of the optic tectum neuropil, it appears that the functional topography of the retinal ganglion cells is arranged in populations that are distributed according to different sensitivity tuning properties. Thank you so much for listening. If you have any questions, please feel free to pop them in the chat box or book a meeting.